Good morning to all. So today, this is the chemical reaction engineering to fluid reaction. In that, we see the rate equation for instantaneous and fast reaction. In the previous lecture, already we have seen the some kinetic regimes. In this case A to case H. Okay, instantaneous reaction, fast reaction, intermediate reaction, and slow reaction. Okay, so this kinetic regimes, where is the actually the rate of reaction is occurs. Okay, in a gas, in a liquid film or liquid film and bulk of the liquid and bulk of the liquid. Okay, so case A, B, C, D, instantaneous and fast reaction. Okay, this reaction rate. Okay, reaction will be occurred in a liquid film, and intermediate type of reaction will be occurred in a bulk liquid film as well as bulk of the liquid, and slow reaction will be occurred in the bulk of the liquid. So we'll see the how to determine the rate equation for instantaneous reaction and fast reaction. So we see this rate equation for instantaneous reaction for the case A and B. Okay, when two fluids are coming in contact, that is the gas and liquid, then interface is formed. This is the gas side and this is the liquid side. So this gas film and liquid film is formed here. Okay, this interface between the gas film and liquid film is formed. A is the partial pressure of A in the main body of the gas, which is diffused through the gas film, and this PAI, that is the partial pressure of A at the interface in the gas film. Okay, this A is dissolved in a liquid, and this concentration of A is measured at the interface is the CAI in a liquid film. Okay, so this means partial pressure of A and concentration of A at the interface in the gas film is the PI, and in the liquid film is the CI, and these PI and CI are assumed it is in equilibrium by Henry's law, that is PI is equal to HAI into CAI. So at the interface, this is the relation PI is equal to HAI into CI. That is the HI is the constant, so PI is equal to HA into CAI. Okay. Now this is the reaction plane. Reaction is occurred at the reaction plane in instantaneous type of the reaction. Okay. So this CA means CAI is the concentration of A is measured at the interface in the liquid film. This A is again diffused through this liquid film towards the reaction plane. This X is the diffusion path of the A in a instantaneous reaction. Okay, and total thickness of the liquid film is the X0. Okay, and this CA at reaction plane, this concentration of A or is measured is the 0. Why it is 0? Because this CB is the concentration of B of in a bulk of the liquid or main body of the liquid. Okay, which is diffused to the liquid film, towards the reaction plane. And this reaction plane, now this is the diffusion path of the reaction plane, is measured is the X0 minus X, X0 minus X. Okay, and this here at the reaction plane, this is the instantaneous type of reaction. A and B coming in contact, and what happened? This all the A and B is consumed here, and this concentration is dropped to 0. So this is at equilibrium. This concentration we consider it is the 0. Okay. Now we apply the mass transfer diffusion rate equations. Okay, and KAG is the mass transfer coefficient of A in the gas film, KAL is the mass transfer coefficient of A in the liquid film, and KBAL is the mass transfer coefficient of B in the liquid film. Okay, so these interface mass transfer equations we use. Okay, so consider equation that is the A plus B to give the product. Okay, so minus RA is equal to minus RB upon B. Okay, this is the stoichiometric coefficients, this relation, okay, of the rate in terms of stoichiometric coefficient. Okay, so this relation we written here by using this rate equation. Okay, so this rate of disappearance of A and B, okay, related to each other by the stoichiometric coefficient B, and this rate with respect to mass transfer we write. Okay, in a gas film, this minus RA is equal to, that is the KAG into PA minus PI means here. Okay, PA minus PAI. Okay, and KAG is the mass transfer coefficient. Same way, in the liquid film, this K equation, that is the RA is equal to KAL into CI minus 0, means this, okay, this KAI minus 0, okay, which is equal to, now this is for the A, now for the B, that time, which is equal to, this equation is the related like this, minus RA is equal to minus RB upon B. So for, with respect to B, we return, which is equal to minus RA, means divided by B. So we write the divided by B here, and this minus RB is the KBL into CB minus 0. Okay. Now these two terms are here, x naught upon x and x naught upon x naught minus x. In the A in the liquid film, see here, this is the diffusion path only x of the A diffuse in the liquid film, but total diffusion, total length of the liquid film is the x naught. Now KAG is measured, KAG is equal to DAL upon x naught, that is the liquid film thickness. Okay, so this x naught we remove it, so multiply by x naught divided by actual length of the diffusion is the x. So DL upon x naught into x naught upon x, and DL upon x naught means that is the KAL. Okay, a similar way, so we multiply here in the first, that is the term is the x naught upon x. Now in the liquid film for the component B, when B is diffuse and the diffusion length is the x naught minus x, but liquid film length is the x naught. So KBL we consider, that is mass transfer coefficient. KBL means which is equal to DBL upon x naught. But this x naught is not a total diffusion path. So multiply by x naught we remove, divided by, that is the actual diffusion path is the x naught minus x. So DBL upon x naught is the KBL. Multiply by x naught upon x naught minus x. Okay, so x naught minus x, this is the actual length of diffusion. Here is also x is the actual length of the diffusion, okay, of A. This is for P. Okay, so this is the equation 1. Now where Kg, Kl and Kbl are the mass transfer coefficient in gas and liquid phase, x naught is the whole film thickness. Okay, so this, and then this is the equation 1. Okay, now this is the rate equation, but in that this PAR, this CAR, and this x naught, this x, okay, these are the unknown. So overall equation, whatever your equation, right rate equation, it must be in the form of the known quantities, that is Kg, Pa, Cb, Kl, Abl, whatever. Okay, so by Henry's law, using this PAI is equal to HA into CI, this equation 2. Okay, so this equation 2, 1 and 2, using of the unknown. So for the transfer coefficient A and B are related by KL upon KBL, means what is KL? DL upon x naught upon DBL upon x naught. So which is equal to DL upon DBL. Okay, DL means that is the diffusion of A, diffusion coefficient of A in liquid film, diffusion coefficient of B in liquid film, equation 3. So eliminating the unknown, that is the x naught, PI, CI in equation 1, 2 and 3, we get, okay, from equation 1 we get that is KL into CI minus 0 x naught upon x, which is equal to KBL upon B. These two equation means here this equation KBL upon these two equation, equating this, okay, CB into x naught upon x naught minus x. So see, from this equation what we calculate? CAI, okay. So here CAI we calculate, which is equal to this x, we write this side x upon x naught minus x, this x naught is the cancel, into KBL upon KAL, this KBL upon KL into CB upon B. Okay, so CI, which is equal to, rearrange this equation, x upon x naught minus x. What is KBL upon KL? From equation 3, that is DAL upon DBL, means DBL upon DAL into CB upon B, equation 4 we get. So again, this first two equation, okay, this first two equation, that is minus RA equal to Kg into Pa minus Ki and KL into Ci minus 0. This equation, okay, we consider. So this Kg into Pa minus Pi equal to KL into Ci into x naught upon x. Okay, so this x naught upon x we calculate here, from x naught upon x we calculate. Okay, from this equation we get this Kg into Pa minus Pi upon KL into Ci. So from this equation, so this equation, see equation 4 is the CAI value, and x upon x naught minus x is there. So from this we can try to calculate this from this equation. This x0 minus x upon x means subtracting denominator. Okay, so x0 minus x upon x, which is equal to kg into pa minus pi minus ka into ci upon kl into CAR, equation number 5. So this equation 5 from equation 4, earlier equation 4 and 5, we obtain CAI, which is equal to, so this x0 minus x upon x, so we write that is the x upon x0 minus x in earlier equation. So this in earlier equation, this here x upon x0 minus x in equation 4. Okay, so we write this, take the inverse of this equation. So we write KL into CI upon KG into P minus PI minus KL into CI into dVL upon dL into CB upon B. So this equation, CI is the cancel here. So solving this equation, we obtain again here to calculate the CAI you calculate. This is the only unknown. Okay, so PI we put HA into CI in this equation. Okay, and calculate this equation, solve this equation by this way. So we get the minus CI, which is equal to this KL into dVL upon dL into CB upon B minus KG into P upon KG HA plus KL, equation 6 we obtain. Okay, so CAI, this value we calculate here, and this is all the unknown, all the known terms. Okay, so this equation 6 we put in equation 1 because here CAI we remove. So minus R is equal to Kg into Pa minus Ha into Ci. So this CAI, Pa minus Pi, what is Pi? Pi is equal to Ha into Ci. So this Ci from equation 6 we put. So minus R is equal to Kg into Ha into Pa, rearrange equation. Okay, Ha we take common, Pa upon Ha minus Ci. Equation 6 put here. Okay, this Ci value. We obtain this equation, minus R is equal to Kg into Ha, P upon Ha plus this. Okay, and solve this equation. Solve this. So this Kg into Ha plus Kl. Okay, we take the LCM of this equation and multiply this P upon Ha here. Okay, so some terms will be cancelled. We obtain this minus Ra is equal to Kal into P upon Ha plus dBl upon dL into CB upon B upon 1 plus KL upon KAG into HA. Again rearrange this equation. Okay, divide by KAL to numerator and denominator to this equation. So we obtain minus RA is equal to dBl upon dL into CB upon B plus EA upon HA upon 1 upon HA into Kg plus 1 upon KAL. So this is the equation we obtain, that is minus R is equal to minus 1 upon S into dNA upon dt. That is the minus R, definition of rate of reaction. Okay, S is the surface, which is equal to dBl in this equation, dBl upon dL into CB upon B plus K upon HA upon 1 upon HA into Kg plus 1 upon K. This is the equation A. Okay, so this is the important equation. Okay, so this is the for instantaneous rate of reaction. So rate of reaction for the type of case A and B. Okay, so here this case A and B. Case A means we obtain this equation we write 1 upon HA into Kg plus 1 upon K. This is the resistance. 1 upon HA into Kg means 1 upon Kg. That is the mass transfer resistance in the gas stream. And 1 upon KAL, that is the mass transfer resistance in the liquid stream. Okay, so here case 1 we see, this is the equation we obtain. Now case in that case, in this case, suppose because there is a mass transfer, this gas phase resistance is controlling and liquid phase resistance is controlling. There are two controlling steps are there. So for negligible gas phase resistance means suppose KAG is the infinity. KAG is the infinity. Okay, KAG is infinity means 1 upon KG is the nearly equal to 0. Okay, nearly equal to 0 means there is a negligible gas phase resistance. Negligible gas phase means there is a no resistance offered by the gas stream. So the rate of reaction is controlled by only by the liquid film resistance, and liquid film resistance is a very more than the gas film resistance, and gas film resistance is negligible. This is the case 1 we see. If this is like this, then this term is nearly 0. So only remaining this 1 upon K. So this equation we can rearrange. So minus R is dV upon dx, Cv upon V plus Pa upon Ha, 1 upon Ka. Because Pa is now if gas film resistance is there is no of the resistance, then Pa is equal to Pai. Pa is equal to Pai because there is a more diffusion, very infinitely diffusion rate is there. Mass transfer rate is very high in the gas film. So in the bulk of the liquid and in the at the interface, this partial pressure of A is the same. So Pa is equal to Pa. Okay, this right here, Pa upon Ha. Okay, which is equal to Bl upon del into Cv upon V plus Ha into Cai. What is Pi? Pi is equal to Ha into Ci upon Ha. 1 upon K. This Ha will be cancelled. So this equation we can write minus R is equal to Kl. Okay, we take the this Kl right here. Okay, into dBl upon dl into Cv upon V plus Cai. And Ci we take the common. So minus R is equal to Kl into Ci into this bracket dBl upon dl Cv upon V into 1 upon Hi plus 1. Equation 7. So this is for the case 1. If gas phase is resistance, negligible resistance, and liquid film is controlling resistance, then this equation obtained. Okay. So this equation, in this equation, we obtain, we write this another term is the enhancement factor. So what is enhancement factor? That is it is the ratio of rate with reaction to the rate for mass transfer alone. Okay. So rate with reaction and rate for mass transfer alone, this ratio is called as the enhancement factor. So from equation 7, this we can write this bracket term, that is dBl upon dl into Cv upon V into 1 upon Ci plus 1. This term is the consider the E. E means what? That is the rate with mass transfer. Okay, enhancement factor is there, and this enhancement factor means rate with reaction. Okay, and this rate with mass transfer alone, that is minus R is equal to K into Cai into E. Okay, so this minus R is equal to K into Ci into where E is equal to 1 plus dBl upon dl means this term. Okay, Cv upon V into 1 upon Cai, equation 8. So this is the enhancement factor. Remember this enhancement. What is the enhancement factor? This is for case 1. If the case B, for the case B equation, what we write when Cb is high. When Cb is high means what? Okay, that is the case B, instantaneous reaction with high Cb. Then Kag into Pa is less than or equal to Kbl upon B into C. Is less than or equal to Kbl upon B into Cp. This is the condition. Remember this condition is very important. Okay, what is the condition? Kag into Pa, that is the mass transfer coefficient. Okay, means the rate in a gas film is less than or equal to this the rate in a liquid film. Okay, so of B. So okay, so this diffusion in a gas film is less than diffusion of B in a liquid film. Okay, so this is the condition for the when Cb is high, because Cb is very high, is not equal. It is a difference in that, because B is this is the greater rate of mass transfer of B as compared to the A. Okay, means the resistance offered by the A is higher as compared to the resistance offered by the liquid film of the B component. Okay, from this condition combined with equation requires that the reaction zone moves to and remain at the phase control, because B is a very high. Okay, so when this B is very high means already we are seeing in the case B, this reaction plane is moves towards the interface. Okay, so A is diffused only in the gas film, and gas film is controlling state only. So A is diffused in the gas film, and this A is when reaction plane is moves to the interface means A is entered in the liquid at the interface and react immediately to the component B and product is formed. Okay, so only gas film means A is not entered in the liquid film. A is not entered in the liquid film. At the interface it is a react and product is formed. So this gas film is only one option is there, offer the resistance, and gas film is resistance controlling step when B is very high. Remember this. Okay, so this gas film is controlling. So and the rate is not affected by any further increase in concentration of B, and it is depend on the only component A. So minus R is equal to minus 1 upon S into dN upon dt, which is equal to KAG into PA. That is the equation B, and this is the equation for the case B. When Cb is high and gas stream is resistance controlling, using the simple equation, rate minus R is equal to Kg into P. But when the liquid film is resistance controlling, when by this condition we identify which one is. Suppose this condition is satisfied, Ag into Pa is less than or equal to Kbl upon B into Cb. Okay, then this gas film is resistance controlling, then using this equation. If this is a opposite of this, if Kg into Pa is greater than this Kbl upon B into Cb, then liquid film is resistance controlling. And for liquid film resistance controlling, using this equation, this A, that is minus R is equal to Bl upon Bl into Cb upon B plus Pa upon Ha upon 1 upon Ha into Kg plus 1 upon K. Remember this equation, okay? So this equation is required for solving the problem or designing the tower, absorption tower, okay? So this is the for case A and B. Putting this. Now similar way to determine the rate equation for the fast reaction. And for the fast reaction, rate equation for the fast reaction for case C and D. So the case C for fast reaction second, and it is the second order reaction. So A plus B to give the product. Okay. And so second order reaction of A and B means minus RA, which is equal to minus 1 upon V into dN upon dt, which is equal to K into Ca into Cb. K into Ca into Cb. It is depend on the bulk of the liquid, which is equal to K into Ca into Cb, this rate. Okay, this is the second order rate constant K. So for gas and liquid film, minus R is equal to this mass transfer rate, which is equal to Kg into Pa minus Pi, which is equal to Kl into Cai into E. This previous equation, equation number 8, that is the in terms of enhancement factor, Kal into Ci into E. Okay, this equation. So this 9, 10 equation be there. So from this equation, we eliminating, that is the Ci and Pi from this equation. So from equation 10, we eliminate it using this equation here. Okay. So this Kag into Pa minus Ha into Ci, which is equal to Kl into Ci into E. So Kag into Pa minus Kag into Ha into Ci, which is equal to Kl into Ci into E. So from this solving this equation, we calculate the Cai. Ci is equal to Kg into Pa upon Kg into Ha plus Kl into E. Equation number, okay, that is Cai. We calculate, and this Ci put in this equation 10. Then we obtain this. So minus R is equal to Kg into Pa minus Ha into Ci. This previous equation Ci we calculate here, put here, okay, and rearrange this equation or simplify this equation. We obtain this. We obtain this equal to Kl into Pa into E upon Ha plus Kl into Kg into E, or which is equal to dividing this Kl here, which is equal to Pa upon Ha into Kl into E plus 1 upon Kag. Okay, Ha upon Kl into E, that is the resistance in liquid film, plus 1 upon Kg, that is the resistance in a gas film. Okay, this total summation. So minus R is equal to Pa upon this 1 upon Kg plus Ha upon Kl into E. This equation C is the for case C. For this is the rate of reaction for the case C, fast reaction. Okay, second order rate. And if Cb is high, that is the case D. When B is high, then the reaction is pseudo first order reaction. And pseudo first order reaction is minus R is equal to K into C into Cb. Means Cb is very high. K into Cb. We consider here K into Cb. That is another constant is the K1. Because this rate of reaction is not depend on the B concentration of, because B is a very high. When increasing B, there is a no effect on the reaction. So we consider it is a constant during the reaction. So K into Cb is another constant is the K1. So K1 into Ca. And this is the called as pseudo first order type of reaction, K1 into Ca. So in which enhancement factor, what is enhancement factor is simple expression, that is E is equal to root of DLN, K root of DL into K into Cb upon KAL. Okay, which is equal to, this is the equation, DAL into K into Cb upon KAL. Okay, K into Cb means that is the K1 root of K DL into K1 upon CAL. Okay, so this enhancement factor equation we consider. Okay, so this equation we calculate using previous in the instantaneous reaction where E is there, we calculate. Okay, so using this equation, this expression we write from this enhancement factor. Okay, definition. So minus RA, which is equal to, that is the PA. So this E in previous in equation C, this E means we calculate here. This E will be that root of dl into K1 upon KL. Okay, so minus R is equal to PA upon 1 upon Kg plus HA upon dl into root of dl into K into Cb. Okay, or K into Cb means that is the K1. And this is the equation D. Okay, for case D. Okay, case D means, what is the case D? That is the rate of reaction for the fast reaction with high Cb. Means the reaction is the pseudo first order type of the reaction. So all these case A we are seeing, case B we are seeing, case C and D means instantaneous reaction rate and fast reaction rate. Okay, so sometimes the derivation asked in the examination, or this equation are important for solving the problem in designing the tower. Okay, so question, these are the important questions are there. That is the derive the rate equation for instantaneous reaction of fluid reaction. Okay, so see case A and B we can explain here and calculate this minus RA. Okay, so for case gas stream controlling step and liquid stream controlling step, both we can explain and to determine the rate equation. Okay, then then question number 2, derive the rate equation for fast reaction of fluid reaction. Okay, so again for the case C and case D we can explain here, and case C rate equation will be determined, then calculate the E and E put in the equation C, and then calculate the rate of reaction for the case D. Okay, so these are the important questions, and these important formulas you must be remembered. Okay,